Why is there a dipole moment? Uh-oh. Because you got a positive charge here, you got a negative charge here, da-da-da-da, they're lollygagging along the way. You put an electric field, and they turn and separate, right? Turning and separating, or even if they don't turn, if they just separate, okay? There are sometimes, the turning is not as critical as the movement apart. Sometimes it is, I shouldn't say that. That's completely false. Scratch that from the record, okay? I'm not sure, I don't know. Yep, scratched it, okay? Stricken from the record. You separate plus and minus and you get a dipole moment, because a dipole moment is in fact charge times distance. And if you separate a charge through a distance, the first thing you get is a dipole moment, okay? Now the picture is not going to be little vectors because of the charge from minus to plus. What you'll have here is if you put some sort of magnetic field or do whatever, what you'll have is little loops. Look at that, those are loops, eh? The orientation of the little vector depends on the right-hand rule, and the magnetic moment per unit volume, which we call the magnetization, is 1 over dV. Sum over all the little magnetic moments divided by, that's it. Divided, we already got it.
So they don't change the orientation of the dipole, they just add that, that's when you get the loop.
This is a completely different picture, and I'm about to expand upon that, okay? In this case right here, you got molecules, you put an electric field, you separate charge. When you put a magnetic field, what you tend to do is take the charges. What happens when you put a magnetic field on something? You've seen it already. If it's already moving, what does it tend to do? Go around. This is heuristic. This isn't literally true. It goes around a circle, right? What happens when a charge goes around a circle? What do you get?
Magnetic field.
You get a magnetic. You get a current. Okay, you get producing a magnetic dipole. Anything moving around a loop produces a dipole. Generally, unless I'm mistaken, very few things have magnetic dipole moments as is. You have to do something to them. I wish I knew more about materials. I'm just not that much of a material. You know who would know this? Robert Kennedy and Dr. Stamp. Dr. Kennedy and Stamp know a lot about this.
Aren't lodestones one of those? Because lodestones made the first compasses?
Probably. That's why there's just not that much stuff out there naturally, though.
Yeah.
Lodestone's a good name for a band.
Yeah.
Okay.
You know?
It does sound
Better
like
than Nickelback.
Nickelback is horrible. If you can listen, if anybody can listen, I should say this for the record. Every time I hear a Nickelback song, I think, boy, that song would be really good if someone took some ice picks and thrust them through my eardrums. Other than that, I can't listen to it.
You're Canadian.
Yeah, that's you know. That, and I know they're Tallahassee boys, but that guy from Creed who sings that really overly dramatic rock and roll style, you know, with that big, deep, booming voice.
Yeah, they talk about
Okay, it is terrible. So let's figure out how big, roughly, in the same way we figured out the dipole moment, the rough estimate of the dipole moment. How big is a magnetic monopole? How big is the dipole moment from, let's say, an atom? Okay? So what I know is, and we'll do this calculation very quickly. All right, suppose something's going around a loop. So we're going around in a circle. Okay. And I have all these numbers written down. What are the units, first of all? Well, area times current, so it's meter squared times, or however, meter squared times amperes. Okay? So we'll go ahead and say, all right, let's see what we can work out here. First of all, M, the magnetic moment of something is, there's the 1/2. I should have put the 1/2 over here. Sorry about that.
It
1/2.
doesn't go with A?
It doesn't go with the A. Okay?
Oh yeah, it's here now.
Yeah. Is it?
Mm-hmm.
Okay. Yeah, there you go. Okay. So is that from,
That's from chapter 9.
that's from chapter 8 or chapter 9?
No, okay.
You're too far ahead already. All right. So I'm going to do this calculation using, not the notes, but because it's all qualitative anyway, let's see if we can associate some numbers here. Here's R cross J, which is R cross, in this case, IDL. And we've already done this calculation before. See, this is hope springs eternal, and then you're just disappointed. Are these readers or these prescription glasses? Okay. So we've done this calculation before. This is 1/2 R rho hat cross I dl. Matt Warden, what's dl?
DL is the vector along the.
No. I mean in this particular case.
Oh, it's v hat. D phi
R d phi, because you need a distance, right?
Yeah. And then
Phi
phi
hat.
here.
Yes? And you're integrating then over d phi from 0 to 2 pi. This is then 2 pi r squared k hat, 1/2, 2 pi r squared k hat, huh? So this is times I times pi r squared, right? See? I times pi r squared, which is I times the area, k hat. Huh? No, we've done that. Listen, there's a reason I do this calculation 3 or 4 times. You got to know that one. That's the magnetic moment of a dipole due to the magnetic dipole moment due to a circular loop. What shape did you guys do in the homework? Circle. It's a square, right? It's a square. They can make you do a rectangle on the exam. Okay? Perhaps not. So we know that. Now let's talk about how big everything is here. I have M, magnetic moment, K hat. Let's get some. Let's just go ahead and get some rough estimates to see how big any one of these things is. First of all, the area I know. The electron out here is on the order of a few angstroms. When you have the hydrogen atom, the electron around a hydrogen atom is, loosely speaking, about an angstrom away. It's a little bit less than that, okay? Now, oddly enough, or I don't know, maybe not so oddly enough, if you think about how much bigger iron is that has an electron circulating out there that gives you a magnetic moment, it's not all that much bigger. You can really, these electrons really pack in very easily, and so we're just going to go ahead and say it's 5 angstroms out. A typical 5 angstrom. Anybody got the interweb working? Yeah. Can you check something for me?
Mm-hmm.
Check the distance, electron, outer shell, iron. I like having the internets. That's pretty neat, huh? Just type
Say ion.